Good day, everyone. My name is Abigail D. Cordero, and in this video, we are going to talk about the concepts of probability and statistics in hydrology, specifically on the topics regression and correlation.
What is correlation, if you may ask? Correlation is defined as the statistical association between two variables. In many studies, we measure more than one variable for each individual. For example, we measure precipitation and plant growth, or number of young with nesting habitat, or soil erosion and volume of water. We collect pairs of data, and instead of examining each variable separately, we want to find ways to describe bivariate data, in which two variables are measured on each subject in our sample. Given such data, we begin by determining if there is a relationship between these two variables. As the values of one variable change, do we see corresponding changes in the other variable? We can describe the relationship between these two variables graphically and numerically. We begin by considering the concept of correlation. A correlation exists between two variables when one of them is related to the other in some way. A scatter plot is the best place to start. A scatter plot or scatter diagram is a graph of the paired x and y sample data with a horizontal x-axis and a vertical y-axis. Each individual x and y pair is plotted as a single point. A relationship has no correlation when the points on a scatter plot do not show any pattern. A relationship is nonlinear when the points on a scatter plot follow a pattern but not a straight line. Our relationship is linear when the points on a scatter plot follow a somewhat straight line pattern. This is the relationship that we will examine. Linear relationships can be either positive or negative. Positive relationships have points that incline upwards to the right. As x values increase, y values increase. As x values decrease, y values decrease. For example, when studying plants, height typically increases as diameter increases. Negative relationships have points that decline downward to the right. As x values increase, y values decrease. As x values decrease, y values increase. For example, as wind speed increases, wind chill temperature decreases. Non-linear relationships have an apparent pattern, just not linear. For example, as age increases, height increases up to a point, then levels off after reaching a maximum height. When two variables have no relationship, there is no straight line relationship or non-linear relationship. When one variable changes, it does not influence the other variable. Now let us talk about the linear correlation coefficient. Because visual examinations are largely subjective, we need a more precise and objective measure to define the correlation between the two variables. To quantify the strength and direction and the relationship between two variables, we use the linear correlation coefficient that is flashed here on the screen, where x and sx are the sample mean and sample standard deviation of the x's, and y and sy are the mean and standard deviation of the y's. The sample size is n. An alternative computation of the correlation coefficient is the linear correlation coefficient is also referred to as Pearson's product, moment correlation coefficient in honor of Carl Pearson, who originally developed it. This statistic numerically describes how strong the straight line or linear relationship is between the two variables and the direction, positive or negative. The properties of R. It is always between negative and positive 1. Second, it is a unitless measure, so R would be the same value whether you measure the two variables in pounds and inches or in grams and centimeters. Third, positive values of R are associated with positive relationships. And lastly, negative values of R are also associated with negative relationships. Let's talk about regression. Once we have identified two variables that are correlated, we would like to model this relationship. We want to use one variable as a predictor or explanatory variable to explain the other variable, the response or dependent variable. In order to do this, we need a good relationship between our two variables. The model can then be used to predict changes in our response variable. A strong relationship between the predictor variable and the response variable leads to a good model. Our model will take the form of this formula where O is the y-intercept, B1 is the slope, x is the predictor variable, and y an estimate of the mean value of the response variable for any value of the predictor variable. The y-intercept is the predicted value for the response y when x is equal to 0. The slope describes the change in y for each one change in x. Let's look at this example to clarify the interpretation of the slope and intercept. First example, a hydrologist creates a model to predict the volume flow for a stream at a bridge crossing with a predictor variable of daily rainfall in inches. Y is equals to 1.6 plus 29x. The y-intercept of 1.6 can be intercepted this way. On a day with no rainfall, there will be 1.6 gallons of water per minute flowing in the stream at the bridge crossing. The slope tells us that if it rained 1 inch that day, the flow in the stream would increase by an additional 29 gallons per minute. If it rained 2 inches that day, the flow would increase by an additional 58 gallons per minute. We have another example. What would be the average stream flow if it rained 0.45 inches that day? Y is equals to 1.6 plus 29x is equals to 1.6 plus 29 times 0.45. That would be equals to 14.65 gallons per minute. In regression analysis, regression is a statistical method used in finance, investing, and other disciplines that attempts to determine the strength and character of the relationship between one dependent variable, usually denoted by y, and a series of other variables known as independent variables. The fitting of a straight line may be done objectively by one of the following statistical methods. A. The method of least squares. B. The method of moments. And C. The method of maximum likelihood. But the common method is the method of least squares. Two variables y, dependent, and x, which is independent, can be correlated by plotting them on x and y axis. If they are plotted on a straight line, there is a close linear relationship. On the other hand, if the points depart appreciably without a definite trend, the graph is called a scatter diagram or plot, which we have discussed a while ago. If the trend is a straight line, the relationship is linear and has the equation y is equals to a plus bx. Number of lines can be obtained depending on the values of a and b. The method of least squares is used to select the line that fits the data best. The principle of least squares states that the best line for fitting a series of observations is the one for which the sum of the squares of the departures is minimum. A departure is the difference between the observed value and the line. Since x is the independent variable, the departures of y are used as where n is equals to the number of pairs of observed values of x and y. The most commonly used statistical parameter for measuring the degree of association of two linearly dependent variables x and y is the correlation coefficient, where delta x is equals to negative x minus x, and delta y is equals to negative y minus y. Here is the standard deviations of x and y, respectively x. Y is equals to middle of each class interval, respectively. If r is equals to 1, the correlation is perfect, giving a straight line plot. which is in a regression line. R is equals to 0, no relation exists between x and y, which is in this scatter plot. Here is 1 indicates a close linear relationship. If a linear regression cannot be fitted, a quadratic parabola can be used as the fitting curve given by y is equals to a plus bx plus cx squared. From the principles of least squares, a, b, and c can be obtained by solving the three normal equations, where n is equals to number of pairs of observed values of x and y. The variables x and y, for instance, may be precipitation and the corresponding runoff, or gauge height and the corresponding stream flow, and like that. For the exponential function y is equals to cx raised to the power of m. It can be transformed to a straight line by using logarithms of the variables as logarithmic of y is equals to logarithmic of c plus m logarithmic x. By putting log of x equals to x, log y is equals to y, log of c is equals to a, and m is equals to b, the function and can be solved for a and b, and the exponential function can be determined. Thank you so much for listening. God bless future engineers.